Okay, so last video we started talking about congruences. And so this video will talk a bit more about these congruences and some of the properties they have that help simplify some of our calculations. And just to recap, we say two numbers a and b are congruent modulo n if n divides their difference. So we would write 5 is congruent to 15 modulo 10 because 10 divides the difference, 5 minus 15. Or you can also say that 5 and 15 are in the same congruence class because they leave the same remainder when we divide by 10. And in the last video, we used a property where I said that whenever you're doing arithmetic with numbers, but when you only care about their remainders, you can actually replace any number in that operation that you're computing with any other number in the same congruence class. Right? And again, this is true as long as you only care about the remainders of what you're computing. This is because congruence is an equivalence relation. And so let's formalize that statement a bit. Right? When we say that we can replace a number with something with the same remainder, what does that really mean? And so if you remember from high school or grade school, I guess, you had this property where if you had an equation where x equals y, for example, you are able to add the same number to both sides of the equation and still end up with a true statement. Right? So if x is equal to y, you add the same thing on both sides, the left side is still going to be equal to the right side afterwards. It turns out that for congruences, a very similar property holds. If you look at the first property on this list, given that a and r are congruent modulo n, right? They have the same remainder modulo n, and that b and s are congruent modulo n as well, it turns out we can do the same operation of adding to both sides to get a true statement, which means a plus b will have the same remainder as r plus s modulo n. And this kind of makes sense, right? So if you think about it, you could say like 5 and 15 modulo 10 have the same remainder. They both have remainder 5. 23 and negative 7 also have the same remainder modulo 10. If you add them, what do you get? Well, again, since we only care about the remainders, it's pretty much the same thing as adding like 5s here and 3s here. And we know that we're going to end up with something with the remainder 8. And we can check that. 5 plus 23 is 28. 15 plus negative 7 is 8 modulo 10. Right, and so it holds for this example, but how would we actually prove that it holds in general? So the way to do that is you just use the definition of congruence. Right? Again, what does it mean? If a is congruent to r modulo n, this is the same thing as saying n divides the difference a minus r. Also, b is congruent to s modulo n. This means n divides the difference b minus s. And what we want is to have n divide the difference of a plus b and r plus s. Right, but that's pretty simple actually from what we have over here. Since n divides a minus r, then we can write a minus r as k times n for some k integer, right? That's a definition of divisibility. And b minus s can be written as l times n for some integer l. And, well, what do we do now? We could just add the two equations that we have. So adding them, we get the following. A minus r plus b minus s on the left is equal to kn plus ln on the right, right? Where k and l are these integers that we've fixed up here. And so we can just rewrite this as a plus b minus r plus s is equal to k plus l times n, where k plus l is an integer. And so since k plus l is an integer, what this tells us, again, using your definition of divisibility, is that n therefore divides the difference, a plus b minus r plus s. And this proves what we want. A plus b therefore is congruent to r plus s modulo n. Right, so it just takes a bit of manipulation to prove it in this way, using the definition of divisibility and congruence. And you can try it yourself for b and c here. Right? B says you can multiply both sides of congruence as long as you're multiplying by things that are also congruent, modulo n. And c is basically an extension of b, where it says if you're starting with a and r that are congruent, well, you can just multiply both sides by a and by r multiple times, right, to get to the powers here. And so let's look at an actual application. Right? What if we were asked now to compute the remainder when we divide this very large power by 11? Right, so it's 202 raised to the 202nd power. Right, so we're not going to want to evaluate 202 raised to 202. What we want is to use the properties of congruence here to compute the remainder. Right? And I should mention here that to say compute 202 raised to 202 mod 11, right, this is different from our notation from the previous page, a congruent to b mod n, where the mod operator or description is inside the parenthesis. Here, mod is actually an operator. It tells us to compute the remainder when 202 raised to 202 is divided by 11. Right, so in general, if I say, what is a mod b without the parenthesis, this means what is the remainder when a is divided by b. Okay, so what do we do here? Well, maybe we can first look for a number that's smaller than 202, but it's in the same congruence class, modulo 11. Well, in the congruence class of 202, right, so all these numbers that have the same remainder when you divide by 11, the simplest one there is going to be, well, whatever the remainder is when you divide 202 by 11. So what is 202 divided by 11? Right, so we can write it in this way using the division algorithm. It's quotient times 11 plus the remainder. And it's easy to see here that it's 18 times 11 is 198, and the remainder is 4. So 202 is really the same as 4, right? From the perspective of remainders modulo 11. And what this means for us is, by the previous property, 202 raised to 202 is congruent to 4 raised to 202 mod 11. Right? And so 4 to the 202 is going to be easier to evaluate. In fact, here it just suffices to look for patterns. 4 itself is congruent to 4 mod 11. What happens when you square 4? Okay, this is now 16, which is 5 mod 11. And you can keep going here. 4 cubed. 20, right? It's 5 times 4, which is 20, which is 9 mod 11. 4 to the 4th power is 36, which is 3 mod 11. 4 to the 5th power is now 3 times 4, which is 12, which is congruent to 1 mod 11. And so from the pattern that we see here, we can now write 4 raised to 202 as simply 4 raised to the 5th power raised to 40 multiplied by 4 squared. mod 11. And the reason why I'm doing this is because 4 to the 5th power gives me a 1. So I don't need to compute 4 to the 202. Every time I hit the 5th power, it just disappears. So this is just 1 raised to 40. And 4 squared, as we see on the left as well, is 5. Therefore, 202 raised to the 202 is congruent to 5 modulo 11, right? And that's the remainder. Right? And that's the power of these properties. Right? We didn't have to evaluate this big power here. Now, just want to mention here that something weird happens when you try dividing both sides of a congruence. In fact, looking at this example, 39 is congruent to 123 modulo 12, right? Because they both have remainder 3 when you divide by 12. So I can write them like this. They're both in the same congruence class, modulo 12. Okay. But what happens when I divide by 3? Right, so I know I can do that if it's just a regular algebraic equation. Right? So if it's just an equation, not a congruence, I can do stuff like divide both sides by 3, right, in order to simplify my calculations. But what happens when I try doing that with a congruence? Okay, so it's 39 congruent to 123 mod 12. Right, so this is a true statement. If I divide both sides by 3, I'm going to get 13 and 41. And, well, now you can check that the remainder here is 1 on the left. The remainder is 5 on the right. So suddenly you've arrived at a false statement. Right? So something weird is happening here. Maybe you can figure out why. Well, okay, so hopefully you tried figuring it out, but I'll show you using the definition of congruence here that 12 dividing 39 minus 123, coming from the first congruence, does not necessarily imply that 12 divides 13 minus 41. Because what happened was, I've divided the right side of this expression, right, by 3. And what that means is now 12 doesn't divide the right side, because I've removed the only factor of 3 from the right. Right? 12 is 3 times 4, so you need 3 and 4 to divide the right side. So what that tells me is maybe this will work if I have 4 on the left, right? If I removed the only factor of 3 from the right, and by dividing by 3, well, by dividing by 3 on the left, now I can say 4 divides their difference here, right? And now this is going to be a true statement when I change this to 4, because they will both have remainder 1. And so you'll see that here in this property that tells us when you're dividing both sides of a congruence, you can actually do so, right? If it's A times D and B times D on either side, right? So they both have D as a factor, well, go ahead, divide by D. But what happens is, what you end up with is not going to be a statement modulo N anymore. It's going to be a statement modulo N divided by the GCD of D and N. And we saw that again here in the previous page. We were dividing by 3, that's your D, and the GCD of D and N is the GCD of 3 and 12, which is 3. So you have to divide 12 by 3 to get 4. Right, so that's what this property says. Well, of course, if the GCD turns out to be 1, then you do get something that's still true modulo N, right? Because you're just dividing by 1. So I'll give you an example. Let's say 15 is congruent to, let's see, 27 modulo 4. Right, so that's true, because they both have remainder 3 when you divide by 4. If I divide both sides by 3, I still get a true statement. Because the GCD of what I'm dividing by and the modulus is equal to 1.